Hello and welcome everyone to our Group 5 assignment part 2 for Work and Energy, Impulse and Momentum. My name is PAVITHRAN PILLAY, along with my group members Khairunnajwa and MOHAMAD AZHARY. We will guide you through our assignment. Okay, so what is work and energy? Well, work is always closely related to energy. The work energy principle states that if there is an increase in kinetic energy in a rigid body that is caused by an equal amount of positive work done on the body by the resulting force acting on the body. Conversely, a decrease in kinetic energy is caused by an equal amount of negative work done by resultant force. Thus, if the net work is positive, then the particle's kinetic energy increases by the amount of the work. If the net work is done is negative, then the particle's kinetic energy decreases by the amount of work. From Newton's second law, it can be shown that work on a free, rigid body is equal to the change in kinetic energy corresponding to the linear velocity and angular velocity of that body. The work of forces generated by a potential function is known as potential energy, and the forces are said to be conservative. Therefore, work on an object that is merely displaced in a conservative force field without change in velocity or rotation is equal to minus the change of potential energy of the object. So, the formulas that we are going to share shows that work is the energy associated with the action of a force. So, work subsequently possesses the physical dimensions and units of energy. Okay, so next we would like to discuss the definition of impulse and momentum. There are always 4 physical quantities that will be associated with the above title. And those physical quantities are force, time, mass, and velocity change. The force multiplied by the time is known as the impulse, and the mass multiplied by the velocity change is known as the change in momentum. The impulse experienced by an object is always equal to the change in its momentum. In terms of equation, this can be expressed as shown: impulse, momentum change. So, impulse is always equals to momentum change. This is known as the impulse momentum change theorem. So, by integrating the equation of motions, as shown, the principle of work and energy can be written as this equation right here, or this equation, where the total of this is the work done by all the forces acting on the particles as it moves from point 1 to point 2. Whereas T1 and T2 are the kinetic energies of the particle at the initial and final position respectively. So, the particle's kinetic energy plus the work done by all the forces acting on the particles as it moves from its initial to final position is equal to the particle's final kinetic energy. Both kinetic energy and work have the same unit, that of energy. In the SI system, the unit for energy is called joule or J, where 1 joule is equals to 1 Newton meter. The principle of work and energy can also be applied to a system of particles by summing the kinetic energies of all particles in the system and the work due to all forces acting on the system. Impact occurs when 2 bodies collide during a very short time period, causing large impulsive forces to be exerted between the bodies. Common examples of impacts are hammer striking of a nail, a bat striking of a ball, and many more. There are 2 primary equations when solving impact problems. In most problems, the initial velocity of the particles are known, and it is necessary to determine the final velocity. So, the first question used is the conservation of linear momentum applied along the line of impact. This is equation 2. This provides one equation, but there are usually two unknowns, which is VA2 and VB2. So another equation is needed. The principle of impulse and momentum is used to develop this equation, which involves the coefficient of restitution, or E. The coefficient of restitution is the ratio of the particles' relative separation, velocity after impact, which is VB2 minus VA, to the particles' relative approach velocity before impact, which is VA minus VB1. The coefficient of restitution is also an indicator of energy lost during the impact. So that's where we get the third equation, which is the equation definition. The coefficient of restitution, which is E, is V equals to the relative separation velocity after impact divided by the relative approach velocity before impact.
Okay, for the question 1, the mass is 0.5 kg and the Y initial is 0.4 based on the assignment part 1. So this is the free body diagram. The height from A to B is 3.1, and to get the speed at surface B, we can using the principle of work and energy. So by using this principle work and energy, we can get the kinetic energy at A, and by using this formula, half times mass and velocity, which is 0 because the object released from rest, so plus the work done by all force and equal to kinetic energy at B. So we can get the velocity at B equal to 7.8 meter per second. And for the question C, to determine the distance from surface B and where the object landing, we can apply the kinematic relationship, X direction and Y direction. So we can get this equation 1, which is D equal to 6.24 TBC. So for the kinematic relationship in Y direction, we can get, and by using this quadratic formula, we get the TBC equal to 0.0789 seconds. So substitute into equation 1, we can get the distance for D is 0.49 meter. For the question D, we can determine the velocity at the object landing with velocity at C by using principle work and energy. So the velocity at C equal to 8.29 meter per second.
Okay, next we will move to question 2. From the question 2, already given the value, the horizontal velocity v1 is equivalent to the speed of the object just before it leaves the surface at B. From the previous question, which is question 1, we already get that the VB is 7.8 meter per second. So this will equivalent to V1, because we know that the horizontal velocity remains same because there is no acceleration involved in the horizontal direction. Okay. Next, also given the value of coefficient of restitution, which is 0.7, and from our previous assignment, the value for our y0 is 0.4 meter. So we will use this value for this assignment. Okay, so we will move to the question 8. Okay, so the question asks the velocity just after it rebounds. So basically it will be like this. So the ball will bounce into the ground, and then it will rebound from the ground. So we will need to know first the velocity where it bounce to the ground, which is to the ground downward, which is we will put as VCY1. We can put here point C, so it will be more easier for us to understand. And then just after it will move rebounds upward, so we can put as VCY2. Okay, so after we understand the concept, so we first we need to know the value of the VCY, the velocity of the ball once it falling into the ground. So we will use the equation of kinematics equation. Okay, so it will be it will be the VCY squared equal to V1Y squared plus 2 constant acceleration SEY minus S1Y. Okay, so V1Y is here, so 0 plus 2 acceleration. We know that the acceleration equal to the negative gravity, so it will be negative 9.81. So we can put here negative 9.81 in bracket. SCY is here, so 0 minus S1Y, or S1Y is the Y0 here, Y0, so 0.4. So we calculate negative 9.81 multiplied by 2 multiplied by 0.4, we will get 7.848 hour. So we will get the 2.801. So supposedly it will be downward, so supposedly it will be negative 2.801 meter per second, because the ball is moving downward to the ground. Okay, so we already know the VCY1. Next we want to find the value for the VCY2. We can use the formula of the coefficient of restitution. Okay, VB2 minus VCY2 divided by VCY1 minus VB1. So the value of E already given, which is 0.7. VB2 0 minus VCY2 divided by the value is negative 2.801 minus 0. So we get, if VCY2, we will get 0.7 multiplied by negative 2.801 negative 1.61. We can eliminate the negative sign, so it will be 1.961 meter per second. Okay, so basically this is the velocity, the vertical motion of the falling ball. And this is the velocity of ball just after it rebounds. rebounds from the ground. Okay. Okay, next we want to know the maximum height to which the object rises, which is the value of the hash. Okay, so this. Okay, so we already know the velocity of the object just after it rebounds, which is the v2 is 1.961 meter per second. Okay, so this 0.4, and this we want to know the value h. Okay, so first we can apply the formula of conservation of momentum. Okay, so this is the horizontal direction. This direction equal to m v1x equal to m vcx. So we already know that the horizontal value will remain same. So the value will be 7.8 meter per second. Will remain the same. VCX 7.8 meter per second. Okay, so here VCX. Okay, so next we will substitute this value into the vector equation, which is the rebounding velocity of ball at sea. The vector form will be the VC2 equal to 7.8 I, which is the x component, plus 1.61 j, which is y component, meter per second. Okay, so next into the last step, we can substitute into the kinematics equation. So v2 y2 squared equal to vcy2 squared plus 2 constant acceleration s2y minus scy. So the v2y is 0 and the vcy2 is 1.961 squared plus 2 negative 9.81, and the sy2 is h minus scy is 0. So use the calculator. 1.961 squared. Okay, so 3.846 minus 9.81 divided by 2, 19.62 h. So we can get the h here is 3.846 3.846. We get 0.1 Sorry, this will be positive because this will move into here, so it will be positive. So positive, and will divide by 3.846 divide by 19.62 equal to 0.196 meter. So this is the maximum height to which the object rises after the first bounce. So here is 0.1696 meter. Okay, that's all. Thank you.